So today, as a part of lecture number 6, we are going to say the expression for deformation under self-weight in a bar. Okay, so we are going to calculate the deformation expression for a bar due to its self-weight. Okay, so we know generally that when a body is subjected to either tensile forces or compressive forces, it is going to strain and stresses are going to be introduced, and there is a change in length, deformation, isn't it, right? But a body can also deform under its self weight. Okay, for example, you may be aware with the complaint ad, isn't it, right? The people you may have seen that, isn't it? So they just try to hold their a rod at a higher height with their hands in order to just stretch themselves, okay, to become taller, isn't it? So something like that. When a body is made to hang, okay, when one of its end is fixed, what is going to happen is, as the self weight of a particular body is going to always act towards the center of the earth, towards down, it is going to experience tensile forces. Okay, that tensile force that this complete body is experiencing is nothing but its self weight. Okay, so I want to tell you, say this. This is a bar which is fixed at this end, and this is hanging with one end fixed here, isn't it? So now this body is made up of certain material, and this body has this bar has certain dimensions. For example, let it take, it has a cross section of circular cross section, okay, with a diameter of d, something like that, isn't it? Okay, so some length l. Okay, so what would be the self weight of this body? Okay, the self weight is nothing but the load that is acting downward, p, over here. Okay, so P is the force acting downward, that is nothing but the self weight of this complete body. So in order to get the self weight, the simple expression is specific weight, which is equals to weight of body divided by volume of body. So this is what you have seen in your fluid mechanics also. Okay, so I am not just explaining in detail about this, but I hope you remember this. Okay, gamma, specific weight or unit weight or weight density is equals to weight of the body divided by volume of the body. Therefore, weight of body is equals to gamma into volume, isn't it? So if it is a circular sectional cross sectional bar, what is the volume? Volume is equals to area into length, which is equals to pi by 4 d square into L. So pi by 4 d square into L, cross sectional area into length of the bar, gives the volume of the bar. For example, if it is made with a steel or some material, aluminium, put the specific weight of that material over here, you will get the self weight of a particular body. So in this manner, you can actually find out the self weight of any body, okay, coming to a wood, a water bottle, or anything that you can find around you. Okay, you can calculate any body's self weight by multiplying its specific gravity by its volume. Okay, so this is how you calculate the weight of a particular body. Okay, so now in order to derive the expression for the deformation under self load, I have considered this bar of length L and cross sectional area of A. Okay, this section, let it be SS. Okay, SS is the fixed end, okay, fixed section, and the cross sectional area is nothing but A, L is the length. So that is what we have seen over here. Okay, A is the cross section, L is the length, and E is the Young's modulus of that particular element, and this is gamma. Just this is gamma. Okay, density, weight density. Okay, so now in order to derive the expression, in order to derive an expression for okay elongation of the complete bar, in order to simplify that, okay, what I do is I split this bar over here. Okay, I consider only this part. Okay, this part of the beam. So what I do is I find, let's take this as delta x, and at a distance of y from the bottom. Okay, so now as you can see here, this is the length delta x, very small, and this is y. Okay, and y is the distance between the end of the bar to this element which I have considered. So what I am going to do is I am going to find the increase in length or deformation in this small strip. Okay, in this small strip. So then what I'm going to do is I'm going to integrate the increase in length in this small strip with limits x equals to 0, here 0 to up to here. Okay, what is the length? L, isn't it? Let's take this, instead of y, let's take this as x. Okay, let's take this as x. So that is what we have done here, isn't it? Distance of x from the bottom end, we have considered a length dx of the bar. Now draw the free body diagram of this element over here. So this is how it is going to look, isn't it? This is the element dx, okay, which is taken at a distance of x. I'll just split this body, okay, in order to show what are the forces acting on this particular body. Okay, so as you can see, we isolated a length dx of the bar at a distance of x from the bottom end. The free body diagram of this element is as shown in this figure. So as you can see here, change in length of an elementary length delta x is equals to PL by A. So this is a normal formula till now we have seen, isn't it? Delta L is equals to PL by A. So as this is the length delta x, so change in length of elementary length delta x. Okay, we are talking about only change in length in this dx. Okay, later on, in order to calculate the complete change in length, we integrate that. Okay, so what is here? Change in length equals to PL by A. So what is P? L, I know L, A, E. The unknown here is P. What do you mean by P? So P is nothing but the force acting on this element, and which is responsible for elongation of this element. Okay, let me go to the previous slide in order to explain that P which is acting over there. Okay, so this is how we calculate this plus. So take this delta x as very small. Okay, this is very much smaller element. Okay, as for the diagram part, we have drawn a little big to be visible. Okay, so it is taken at a distance x, and remaining portion is almost L minus x, because this delta x very much small. I did not consider this here. And as you can see at this bar, okay, the length the load, the weight that this element is going to carry is equals to self weight of this portion, not the complete self weight, complete weight of the body, isn't it right? Okay, so if you take this section over here, the load that is taken by this bar at this section is equals to this part which is hanging to this section. If you take anything over here, if you take a section over here, the weight, self weight at this section is going to be the complete, this complete body self weight. If you take over here, it is going to be the complete portion of this. Okay, so whatever the section here is, this section here, so the load that is acting on this is the this shaded portion only, isn't it? What is the length of shaded portion? X. Therefore weight is equals to, we know, gamma into volume, gamma into area into length. What is the length? X, isn't it? Right. So gamma a x is nothing but the self weight of the element. Okay, if you call this as a p, I mean w is equals to p, we are generally denoting it with p, isn't it? Right. So if you denote it with a p, and that p is going to add over this section. Let me just clear. So this is where that p is going to act, which is equals to gamma a x. Okay, so if I take the load over here, it is going to be p is equals to gamma a l, the length. Okay, but as of this derivation, this is the section at which I need to calculate. So that is how I got a x gamma or gamma a x. Okay, so as this thickness is very much small and the same load p is going to have the upwards also. Okay, so now put those values over here. What is the p? Ax into gamma or gamma ax, and l is nothing but length of the element dx, and a divided by e also. Okay, so now a gets cancelled and this is what is going to be reminded now. So you can see this is the change in length for length delta x, this is the change in length in this element, small element. Okay, so now in order to get the complete change in length in complete bar, what I need to do is I need to integrate this equation. So therefore for the whole bar, delta L is equals to integral of 0 to L x gamma dx by a. So why are we doing this integration with ax? Here the variable over here is x, isn't it? Right, x. So what is x at bottom of this bar? 0. And what is the value of x at the top? I mean, let me show you in this. See here, if this strip is at this place, okay, what is x? X is nothing but distance between this section and the free end, isn't it? That is going to be 0. But when this section is here, okay, what is the value at this? X equals to not 0, isn't it? But what happens if a section is here? X equals to L, it is going to be equals to L, isn't it? Right. So x has a minimum value of 0 and a maximum value of L. Therefore the limits are 0 to L. So on integrating, you can just bring these two values gamma and divided by 2e as constants outside, and by integrating this x dx, what is the integral x dx? X square by 2, isn't it? Right. So x square by 2. Okay, so you get value, this value L, I mean apply the limits 0 and yeah, and this is what you get finally. So if W is the total weight of bar, then W is equals to AL gamma. So that is what we have seen earlier, isn't it? Right. So this is the value of delta L. But if W is the total weight in W అనుకుంటే W ఏమవుతుందండి? Gamma into volume, right? AL. So gamma equals to W by AL. Put this value over here, that's it. Okay, then what is happening is delta L is equals to WL square by AL into 2. Cancel LL, get cancelled, and WL by 2 AE is what we are going to see. So this is the formula for increase in length in a bar of any cross-sectional area. If it is a rectangle or circular, any cross-sectional bar, if it is hanging in such a way, the change in length or the deformation in the bar, because if its self weight is delta L is equals to WL by 2AE. Of course, some textbooks this W is represented in terms of gamma also. Okay, no need to worry about that. So now there is another thing that we are interested to find out. That is this maximum stress in the bar. Maximum stress in the bar. So as you can see in this diagram, let me just uh, clear this. See, in this whole bar, okay, as you go upward, if you take a section here, the load taken by this section at this section is only because of this shaded portion, okay, isn't it? But if I take a bar over here, this is the portion that is to be carried by this section. I mean, what is happening is, as you go upward, if the section moving upward, what is happening is the load that it should carry is also increasing. Because of that, as stress is proportional to this force, okay, stress is equals to force by area. Force is, I mean, area is constant, therefore take it out, and stress is proportional to force, isn't it? So now, as your section is moving upwards, the force at that particular section is also increasing. Therefore, what is happening to the stress at that section? It is going to change, isn't it? So let me draw this figure over here. This is how it is going to change as you move upward. Okay, this stress is going to increase, keep on increasing. Where it will be minimum? At this bottom free end. And where it is going to be maximum? At SS. So at SS, the load that is being carried by the bar is maximum, and the stress that is being seen is maximum there. Okay, so now this SS is the section at section of maximum stress. So stress at section XX equals to force by area. So force is nothing but, what is the force? Self weight, isn't it? So here force is nothing but the external any kind of force, it is self weight. So what is the self weight we have seen earlier? What is that? Gamma A into X, but here X equals to L, isn't it? కంప్లీట్ బార్ గురించి మాట్లాడుతున్నాం కాబట్టి గామా ఏ ఎల్. సో గామా ఏఎల్ ఈజ్ ది సెల్ఫ్ weight డివైడెడ్ బై ఏ. సో గామా ఏఎల్ డివైడెడ్ బై ఏ cancel gamma L, and this is nothing but specific weight, and this is nothing but mass density or weight density. Okay, this is weight density or specific weight, and this is mass density. And the relation between gamma and g is equals to, gamma is equals to rho g. So gamma L equals to rho g L. You know the value of g, 9.81 rho into L. So this is the maximum stress at this top fixed end section. Okay, so that is why when you try to hang to something, okay, when you try to hang to something in a park or something, or when you are doing an exercise, okay, what you get is, if you are hanging with your hands, the maximum stress is going to be seen in your hands. Okay, if you are hanging invertedly, I mean legs upwards and head downward, and if you are hanging to something with your legs, your the maximum stress will be in your legs. Okay, so that is what I want to tell you. So I hope you understood. This is a simple expression to calculate the maximum stress, and also the the elongation that is going to take place in the complete body. Okay, so with this I conclude, and there are few problems that are going to come. They are just based on this simple expression. Okay, so no need to worry about those problems.